Okay, good morning. We'll get started. I wanted to start out with another Gauss's law problem. Throw a little bit at you each day before we get into potential. So another infinite sheet problem. So if we've got an infinite conductive sheet, and an infinite insulating sheet, and we want to know what's the so if we're given sigma insulator, we're given sigma insulator is some value and then when the conductive sheet is all alone in space with nothing else around it, -6 microcoulombs per square meter. Okay, so that means that's how much charge density we have on each face of that conductive sheet, -6, when there's no other charge around. Now we're going to bring this insulating sheet of charge up near it. And what's going to happen to our conductor? The charges are going to redistribute. They're going to move around. We're not going to have half on one side and half on the other anymore. They're going to redistribute. So the question is, what is the charge density on each side of that conductive plate? I'll call it sigma left and sigma right. Those are the charge densities on the conductor after the insulator is brought in air. Yeah, I'll post it after this lecture. Sorry, didn't post last lecture video. Just if I forget in the future, just shoot me a reminder email. Okay, so that's the first thing we're going to find. And then what's next? Find the electric field everywhere. That says everywhere. Okay. So this is how I do this problem. I just pretend I have 3 insulating sheets of charge, okay? Because that's fine. I can treat them that way. 3 insulating sheets of charge. So that's the way I started out. So I have one here with sigma L charge density, and I have one here, sigma R charge density, and then I have my insulating sheet over here, sigma insulator, that never changes, right? Now I'll fill in what the electric fields should look like. So let's I'll make this one blue. I should have written it in blue. This one will be blue. So there's some charge on that plate. I'm just going to treat them all like they're positive. And if I do that, then a negative sign will flip the direction automatically later, you'll see. So I'm going to pretend they're all positive for now. I know that can't possibly be true, but I'm just going to go ahead and fill in here. So if there's positive charge on this left face here, what's it going to do? It's going to send an electric field out in this direction, right? And then this direction, right? So I'm going to call that E left. This is the electric field due to the left sheet of charge. And I'll use red for the next one. And it's going to send, if there's a positive sheet of charge at that right face of that conductive plate, it's going to send electric field out in this direction on this side and in this direction on this side, right? And we'll call that E right. And then our insulating sheet, I'll use green. Our insulating sheet, if there's positive charge there, will send electric field out in these directions, right? E insulator. Okay, now I have 1, 2, 3. I have 4 regions, right? This this region of space, I'll call that 1. This one I'll call 2. This one I'll call 3. And this one I'll call 4. So there's 4 places where the electric field might be different. There are 4 electric fields I need to charge. I need to find. Once I find the electric field at this location, it's the same over here. It's the same over here. It's the same out at infinity, right? It doesn't change with distance from an infinite sheet of charge. Once I find it one in that region of space, I know what it is everywhere out there. Once I find it here in this region of space, I know it's the same here. I know it's the same here, right? It's the same everywhere in that region of space between the 2 sheets of charge. So there's one thing I know for certain. I know where what the electric field is in one of these regions of space, don't I? Because it's filled with conductive material, right? In between what I'm drawing as a left sheet of charge and a right sheet of charge, in between those is really filled with conductive material. And so the electric field in that region of space, let me move this down a little bit. The electric field in this region of space has to be 0 because that's filled with conductive material. Okay, so now I just need some equations, right? I have, what do I have? 2 unknowns, sigma left and sigma right. So I need 2 equations. Well, one of them comes from this region of space right here. I can just look and see what's happening in here. That's going to give me one of my equations. E left is going to, let me write it as just vectors. E left plus E right, vector addition, plus E insulator has to be 0. We are inside a conductor. Because we're inside a conductor, right? This is really a conductive, this is the thickness. I'm trying to draw the thickness of the conductive sheet there. We can, as thin as we try to make that conductive sheet, we can't make it one molecule thick, right? It always has some thickness to it. And when we put charge on a conductive sheet, it immediately splits to the 2 faces of the sheet. So I'm drawing it exaggerated here. I'm drawing it with some width to it. So it's a little easier to see what's going on. But this is the width, the thickness of the conductive sheet. And so we know if we're inside of a conductor, E has to be 0. So that's the first thing we know. What else do we know? We also know that the net charge on that conductive sheet can't change during the problem because nothing touches the sheet. There's no place for it to get extra charge or for it to lose charge. So if it started out with, where was it? If it started out with -6 microcoulombs per square meter on one face and -6 on the other face, that's what it started with when it was all alone in space. And then we brought another charged sheet near it. The charge can move around, right? Some of it can go over here, some of it can go over there. It can move from one face to the other, but it can't disappear, right? It can't magically get more charge if nothing touches it. It's isolated. So when we bring that other charge in, the charges can redistribute, but the net charge on that sheet has to be the same. So sigma left So sigma left plus sigma right has to equal whatever charge was on there before. What am I calling it? Sigma conductor. That was given. The reason I don't draw thickness for the insulating sheet is because we know the insulating sheet also has to have some thickness to it, right? But when we put the charge onto that sheet, when we start adding charges to that sheet, we put a charge here, we put a charge here. An insulator, what's the definition of an insulator? The charge can't move. It has to stay right there. So if I put the charge on one face of the insulator, there's nothing on the other face. I can treat it. I really do have a thin, infinitely thin, 1 electron thick layer of charge there because I put it on that face and it stays there. It doesn't move around. So I can draw an insulating sheet like a super thin, infinitely thin, is that a word? I don't know. Thickness. And the reason I can do that is the charges, I put the charges on the surface and they stay right there. They really are on a perfect surface. Whereas a conductor, I put the charges there and then they move around wherever they want. Half of them end up over here, half of them stay on the one face. And so I have to end up with two faces for the conductor. Good. All right, so what do I have here? I have two equations. So I can use those two equations to solve for my two unknowns, sigma left and sigma right. Once I know sigma left and sigma right, then I can solve for the electric fields everywhere. So let's start with the easy one right here. Sigma left. So here's equation number one. Sigma left plus sigma right is equal to 2 times, what did I say it was, minus 6? So that's my first equation. And my second equation comes from the fields. So the electric field is going to be sigma over 2 epsilon naught, right? The electric field coming off of an infinite sheet of charge, an insulating sheet of charge. So if I'm kind of viewing these as infinite insulating sheets of charge, I know E sub L right here has to be sigma L over 2 epsilon naught, and it's pointing to the right. So I'm going to pick a direction here. I'm going to call the right my positive direction. And so if the right is my positive direction, then this is a positive number, sigma L over 2 epsilon naught. And if sigma L turns out to be negative in the end, then I just put a negative number in here and it flips the direction, right? It would be negative something over 2 epsilon naught, which means it points in the other direction. So if you assume positive, and then in the end you find out that they're actually negative, it automatically flips the direction. So that's why I'm assuming, that's why I drew all of these like they're positive, because then it takes care of itself in the end. We know some of them have to be negative, right? Okay, so that's the first one. What's the next one? Sigma right, and I drew it pointing to the left in the negative direction. So I've got a minus negative direction, this vector addition, sigma right over 2 epsilon naught. And then I've got also pointing to the left, E from the insulator. So that's going to be sigma insulator over 2 epsilon naught. And those have to add up to be 0. Remember, the right is my positive direction, vector addition. And of course, what can I do first thing? Multiply through by 2 epsilon naught. So I have sigma L minus sigma right minus sigma insulator equals 0. So that's my second equation. So now I can substitute in from my first equation into my second equation. What can I do here? Oh, I know sigma I. Sigma I is 10, right? So I can substitute that in. That's given in the problem, right? And then now I can substitute in from up above. Sigma left is just equal to sigma left is equal to negative 12 minus sigma r. This is sigma left. Now I can solve for sigma right. So I get, what do I get? 2 sigma right is minus 22. So sigma right is minus 11. And if sigma right is minus 11, and sigma right plus sigma left has to be minus 12, that means the other one has to be minus 1, right? Oops. So now I have this situation, right? I have, this is, this one's plus 10, right? I got a bunch of positive charge here. This one is minus 11. Lots of minus charge there. And this one is minus 1. So a little bit of negative charge there.
Hi, Professor. I have a question.
Okay.
So this is different from for the, I remember before we talked about the conductor ball, then you put 1 point of charge inside, and then the inside of the ball will be equivalent, the magnitude of the point of charge inside. You remember that's the one, so you have Gauss's one, so the inside the, you know, the ball will be equal to 0 because the point of charge in the center of the ball will be equal to the inside layer of the conductor wall.
Yes.
But why this is different? If you look at the density, one is plus 10, one is minus 11. I will be assume this is just like the same in the right side should be equivalent to the insulate sheet. But why this is different? Why it's not a negative 10? Instead is like what?
Because you need E to be 0 in here, right? And if you had 10, if this was minus 10, then it would have a negative, it would have an electric field pointing this way. And the plus 10 over here would have one pointing that way. Those two would cross out, but then you'd be left with this negative 1 in here. You wouldn't have E equals 0. So it's both of these combined have to cancel this one. Or you have two faces. So in our cavity, right, a spherical cavity, the charge inside was creating electric field, and you only had one surface that could negate that. So it was always equal and opposite charge to negate that electric field. But now you have two sheets that have to combine to negate the field from the other one.
Okay. But the ball will be the same, right? Because the point of charge is also generate electric field outside, and then the wall, inside the wall also both sides. And
No.
then the outside also both sides. If you draw the, I'm still a little bit confused. What's the difference between this and that? Yes, please. So that will.
Yeah, so we have this situation, right? Spherical. So we get negative charge around the surface here, and then we're left with maybe positive if that was neutral. I don't know, whatever, doesn't matter. But remember that in spherical symmetry, the charge, just because we have spherical symmetry, we know now, Newton had to invent calculus to prove this for masses, but the charge outside of your location, if you have spherical symmetry, doesn't produce any electric field inside. So if I have an insulator, and I put charges only on the surface of that insulator, all around the surface, it's spherically symmetrically around the surface of the insulator, what's the electric field inside? 0, because when you're inside, you only look at the charge inside of your location. So if I draw my Gaussian surface here, the charge outside doesn't affect what's inside because it's spherically symmetric.
Okay, so the difference is the symmetric, right?
Yeah.
Actually, that's how electric field is just all crossed out, but because it's a sheet, so it cannot cross out. So that way, we only know it's inside the conduct sheet. It should be E equal to 0. That's the only really we can use to.
Correct.
Okay, thank you.
Yeah. Okay, perfect. So this is what we know from doing our two equations. Now we can solve for E everywhere, plugging things in. So we know that E1, this is region 1 over here, right? Region 2, we already know E is 0 there. And then region 3 and region 4. So E1, we need to find so E1 is going to be, this is, forgot what colors I used earlier. Should I be consistent? Blue, red, green. So okay, so the blue one is negative, right? So it's producing an electric field in this direction. I'll call that E left. The other one, the red one, the right face, is also negative. So it, if we're over here in region 1, it's producing an electric field toward the negative charge, right? E right. And sigma insulator is positive. So it's producing an electric field in this direction. So now I know, because I know the charges are positive and negative, I can actually assign the correct directions. So I know that this is going to be in the positive direction. You could do it either way. You could do it. You could just use what you did earlier. Where's our earlier equation? Here it is. We could use this equation, right? And say, I assume that they were all positive, and now I'm going to plug in the actual values, negative signs, positive signs, and they will automatically get the direction right. I could do that. I'll do that first. Let me do that first. So this is, oops, what was this? Minus sign? So that was my equation, right? So I can bring it down here and I say sigma left over 2 epsilon naught minus sigma right over 2 epsilon naught minus sigma insulator over 2 epsilon naught equals E1, right? That was my equation from, nope, that's not my equation. That was my equation for E2. For E1, they're all in the negative direction, right? For E1, they're all in the, boop, there we go. They're all in the negative direction. So that was the equation I got, just assuming they were all positive. Now I can plug in the ones I know are negative. So sigma 1 is actually, sorry, sigma left is actually a -1. See, so that's going to fix the sign. So negative times negative is positive, and I know it is in the positive direction, right? So that's going to automatically correct itself and make that positive. Sigma right is negative, and so I'm going to get a positive there, right? You see that? That's what happened to my E. Things are disappearing here. Okay, and sigma I is positive. So that's going to end up staying negative, and it is negative direction, right? So see how it automatically corrected itself? I came up with this equation here, this one right here, I came up with that equation based on the fact that every one of these sheets was positively charged. And then when I found out some were negative, I just plugged in the negative number and it automatically corrected itself. Negative times negative is positive, and it really does point in the positive direction. It automatically corrected itself. Or if you prefer, you can use these directions here and then use the absolute value of sigma in your equation, because you're assigning the direction. You don't want to double count, right? So I'm just going to do it this way. I've assigned the directions when they were all positive. I've already done that. Why redo it, right? I've already done that here. And now I can just plug in the values for sigmas. If they're negative, it automatically flips it. Treating them as insulators does not necessarily mean they all have to be positive. I just find it easier to assume they're all positive, because then when you plug in the negative sign in the end, it automatically flips it. If you're kind of guessing that some are positive and some are negative, I mean, I guess you could do that too. It doesn't matter. Then when you get some are, then if you're wrong, when you plug in the negative sigma instead of a positive sigma or vice versa, it should correct itself. Is that right? I'm not sure it will, though. Let's see. Because if you plug in a positive instead of a negative, it doesn't correct itself. I think if you assume they're positive and you get a negative, it corrects itself. If you assume it's negative but it's really positive, it doesn't correct itself. Anyway, I have to think about that. But I know when you do it this way, it corrects itself. All right, so there's E1, and then you can just keep doing the same thing for the other ones. What did I get here? I got a minus 10 and a plus, that's plus 1. So plus 1. No. Plus 12 minus 10. Plus 2. Plus 2 over 2. There we go. Which is the same as 1 over. So it's to the right. So there's our electric field in region 1. The electric field in region 2 is 0. We already said that. And then we can go through and find the others. I'll let you do that. I'll tell you what I got. But you can try it later. E3, I got, what did I get for E3? So it's going to end up pointing to the left. And then E4, I got minus 1 over sigma. And these two have to be equal and opposite. Because if you're standing outside looking in, if you have a sheet of charge here and another sheet here, and you're way out here looking in, all you see is a bunch of charge there, right? And if you're standing out here looking in, all you see is a bunch of charge. Like, it looks like one big infinite sheet to you. So if you think about it, when you're outside looking in, it should look the same from both sides. It doesn't matter that the insulator's on the left and the conductor's on the right. There's the same net charge there, spread out the same way. You just add them all up, and you should be able to get the electric field out there. Okay, so That was a little more Gauss's law, and infinite sheets, conductors, insulators. Try that. Then you can, after you've done that one, you can do two conductive sheets. Instead of a conductor and an insulator, do two conductors. So you know what sigma is on each face of conductive sheet 1 when it's all alone in space. You know what sigma is on each face of conductive sheet 2 when it's all alone in space. We bring them near each other. We want to know what are all the sigmas and what are all the electric fields. It's the same problem. You just have you have 4 unknowns, so you need 4 equations, right? But it's the same equation. You get the equations the same exact way. Okay, we ready to jump back into chapter 7 now? All right. Electric potential. So delta V was defined last time as a negative work done by the field over Q. This is the equation I told you that in all of our textbooks, it was written, delta, forgot my V over here, delta V is this. It was always written this way in all the Survey textbooks. Sorry, it was always written this way. That was the equation that was in all the books. And then all of a sudden, I forgot which edition, the 7th edition or something, they changed to this equation. And so I had to change all my notes and everything because they defined the work differently. They said instead of the work done by an external force, it was the work done by the field. So all of a sudden, all the equations, the minus sign changed. So that's why I told you the other day, it's more complicated to try to just memorize the equation to get the sign right, because it's very tricky. Work done by the field, work done by the external force. Is it a positive charge? Is it a negative charge? Is it going to higher potential? Is it going to lower potential? You can make these problems crazy with negative signs if you want to. And sometimes I want to. So the easiest thing is just think about what's happening. Work done is positive when the force is in the same direction as the motion, right? So just think about that. Think about it that way. And I think that's a lot easier than trying to figure out the signs from the equations. But of course, the equations give you the correct answer if you do them properly. Okay, so here's our equation. And I have my -1 over Q. And what's work done by an electric field? It's the integral of F dot ds. Right, that's work done. And what is the force from an electric field? Q times E, right? So let's plug that in there. What do we get? We get -1 over Q, integral of Q E dot ds. So we get minus the integral E dot ds. And that is an important equation. Okay, so this is one way we have now of finding the potential difference between 2 points. If we know the electric field in that region of space, we just take the integral E dot ds from point A to point B, and we can figure out the delta V between those 2 points. Okay. So let's look at a simple case first if E is constant. So delta V is minus the integral E dot ds. So we've got some region of space here. We've got an electric field. We're going from A to B. And some distance, call that D, some distance D, right? Between A and B. So what is this? If the electric field's constant, it comes out of that integral, right? And what is the integral of ds is just the distance between those 2 points, right? So this is just minus E times the distance between the 2 points. This is delta V AB. So what I always do, when I do these equations, I try really hard to get the signs right using the equations, using the math. I try really hard. Sometimes it works, sometimes it doesn't. In the end, I just look at the equation and figure out whether delta V has to be positive or negative. So let's take a look at this. Did we get the sign right or not? This delta V AB is V final, right, minus V initial. So which one has to be at higher potential? A, yes. Why is that? Because last time we had this equation. Where was it? Maybe it wasn't last. There. Oh, there. Oh, there. That that one with the arrows and the stars and the red box. E always points toward lower electric potential. The electric field always points toward lower electric potential. So if the electric field is pointing from A to B in this problem, A has to be higher. VA has to be greater than VB. Since E points always points to lower electric potential. So if A is greater than B, then this must be negative, right? So this is negative ED. We got it correct. It checks out. Got the minus sign right. So I try, when I do these equations, I try to get the minus sign right. Remember, there's a, what is there? There's a dot product here. That might mess you up with a minus sign. There's getting the limits correct on the integral. There's the minus sign out here, right? There's a lot of places to mess up a minus sign. Just the way I do it, I try to get the minus sign right all the way through. At the end, I just look at this and I say, wait a minute, E is pointing this way. I know this has to be negative. If it's not, I put a minus sign there. If it is, I'm good. Okay? I think you'll, in the end, just looking at the situation and trying to get the minus sign right is much easier than trying to get all the minus signs right along the way. But do both. Okay, let's do another one of these uniform electric fields. So we've got our uniform electric field. And we're going from A to B. So this distance is given, and this distance is given. So the key here, this is getting a little more complicated, although it's not too bad because the angle is constant between the line. If we took a straight line path, right, from A to B, if we took a straight line path, the angle between that line and the electric field is constant, so we could have a cosine theta in there from our dot product, right? We have this equation, right? We're trying to use. So we get a dot product, but that it's a constant angle. But there's an easier way to do it. We can take a different path, right? We can break this up because this is linked. Remember, where did this come from? Where did this equation come from? Came from the work done. And what did we do last time? We said the work done on any path between points A and B by the field on the particle that we're moving is the same. The electric field is a conservative force, conservative field. So, so we can take this path, we can go to point E over here. We could take this path, use blue. We could take that path, or we could take the green path, or we could take the straight line path, right? Doesn't matter. Or we could take any curved path if we wanted to. Any of these paths from point A to point B give us the same work done. So the integral up here is going to be the same. So the delta V between points A and B will be the same regardless of the path we take. So if we look at this equation again, delta V is the integral of E dot ds. When our electric field and our path are perpendicular, we get a cosine 90 degrees, we get 0, no change in electric potential. When we move perpendicular to the electric field, there's no change in electric potential. So we call those, I'll use red. So there's going to be a plane here and another one here. I could draw them anywhere, but I'll draw them at A and B. And we call those equipotential surfaces. Anywhere on that red dashed surface, the potential, the electric potential is the same. So moving along the surface, delta V is 0. So this, we call these equipotential surfaces. So anywhere on that surface, the potential is the same. And so delta V AB is equal to delta V AE, and it's equal to minus ED. Okay. Let's take a 10-minute break. and then we'll continue with potential, electric potential. All right, so let's take a look at this worksheet. So we've got two situations, plus Q here, and plus lowercase q here. And so there's a bunch of questions. We're going to fill in a greater than sign, a less than sign, or an equal sign in between these two columns for every one of these. So they've drawn in. So it says, in the questions that follow, decide if the quantity on the left is greater than, less than, or equal to the quantity on the right. Okay. I would start with number 4. Let's do number 4 first. So we can just count field lines, right? Electric field lines. So the ones with the arrows here are the electric field lines coming out. And so this one has 1, 2, 3, 4, 5, 6, 7, 8 field lines. And the other one has a lot more than that, right? So lowercase has more charge than capital Q. Okay, now we'd start from the top, work our way down. So the electric field at capital A versus the electric field at lowercase a. Yes, the electric field at capital A is going to be less than the electric field at lowercase a, because we're the same distance away, right? The radii here are the same. We're this distance away from the charge in both cases are away from the charge. But one of the charges is much bigger than the other one, right? Lowercase q is bigger in magnitude than the capital Q. So we're going to get a bigger electric field there. Okay. How about number 2? Should we do the electric fields first? What do you want to do? How about we go to number 5? While our brains are tuned into electric fields, let's answer all the electric field questions. Number 5, the electric field at B, that's this one out here, compared to the electric field at A, that's that one there. So we're comparing capital B to capital A, and the electric field falls off, right? It gets weaker as we move away from the charge. The electric field lines are getting farther and farther apart, which means the electric field is getting weaker. So B is less than A. Good. How about B and C? B and C, the electric field here and the electric field here. Capital B and capital C. Okay, those are the same. Good. Same distance away from the same charge, right? Same distance away from the same charge. All right, now let's do, are there more electric fields? Lowercase b and lowercase a. We just did that one, but electric field gets weaker as you move away from that point charge, right? Okay, now let's go back up and do number 2. So this would be less than. And if we think about it, if we just go back to our, I know the electric field here is not constant, right? It's changing. But let's just go back to our constant electric field. Yeah, it's a stronger electric field. This distance is the same, right? Remember up here, if the electric field is constant, what is the delta V? It's just the electric field times the distance. So I know this electric field's not constant, but if the electric field, if the distance is the same for both of these situations, and it is, right? The distance is the same for both. We're going from A to B here, and we're going from A to B here. The distance is the same for both of them. But in one case, the electric field is much stronger. So the electric field integrated over the distance is going to be a bigger amount. Okay. How about 3? 3 says capital C to capital B, delta V for that, versus delta V lowercase c lowercase b. And what is it? They are equal, and they are both 0. Number 2. Yeah, we're remember the delta V. Delta V is the integral of E dot ds, right? And if the E is constant, it's just the electric field times the distance. So if the distance is the same in 2 cases, in one case the electric field is bigger, you're going to get a bigger delta V, right? I know the electric field is not constant, but it's the same logic. If you're integrating over the same distance, over the same path, and one electric field is bigger than the other one, then the integral of E dot ds is going to be bigger in that case. So these are 0 because we're on the same, we're moving, if you integrate E dot ds, the dot product gives you 0, right? Because the electric field is perpendicular and we're going this way. Electric field perpendicular, we're going this way, right? We're moving perpendicular to the electric field, so the E dot ds gives you 0. Yes, yes. The electric field is stronger here. You could tell because there are more electric field lines. Yes. And so what do we call these surfaces? Equipotential surfaces. So everywhere on that surface, the potential is the same because we're moving perpendicular to the electric field when we're on that surface. So the electric potential does not change. Okay, good. What do we have? A couple of more at the end. Capital A versus lower. The potential at capital A versus the potential at lowercase a. The potential here versus the potential here. So I'm just going to put the answer here and then we'll talk about it in a minute. Okay. So we'll talk about electric field near point charges in a minute. Sorry, electric potential near point charges in a minute. And then the last one here, what do we got? What do we have? At capital A versus lowercase b. Capital A versus, oh, this is a tricky one. Oh, okay. So let's take a look at that. Do we have that? So we want to know the electric field at A versus the electric field at lowercase b, right? And so we know the electric field near a point charge is K Q over R squared. And this is going to be K little q over R squared. It's, sorry, lowercase b. And we know, what do we know? We know the charge Q is equal to twice, little q is equal to twice capital Q, right? You have to count the field lines, but one has twice as many. And we know that RA, we know that RB is 4 times RA. That's lowercase. That was given somewhere here. One radius is 4 times the other one. Okay. So now we plug these two things in, and this was a given. Okay, now we plug them in, and what do we get? We get KQ over RA squared, and we've got K2Q over 4RA squared. So we get one of them, and is this, and the other one is 1/8, right? So this, the electric field at capital A is larger than the electric field at lowercase b. Okay. Point charges. We got a point charge filling the space around it with an electric field. Got too many. And we're moving from point A to point B. So what's our electric field? K, Q, I'll use a lowercase q, KQ over R squared, right? So the delta V, that's going to be VB minus VA, final minus initial, is minus the integral of E dot ds. So let's plug in what we know. E is KQ over R squared. That we're going to get a dr. We're going to get a cosine 0 degrees because we're moving in the same direction as the electric field points. And we're integrating always from the small number to the large number. And so what do I get? And this is 0, cosine 0. And so I get a negative KQ integral 1 over R squared dr. That's minus 1 over R from RA to RB, right? So I've got KQ 1 over RB minus 1 over RA. And this is VB minus VA, right? Did I get my signs right? Let's check signs. This one must be negative or positive. VB minus VA. VB minus VA. We're going from A to B. VB minus, there we go. So the electric field points in this direction, right? The electric field points radially outward from that point charge. So it points from A to B. Electric field always points toward lower electric potential. So VB has to be less than VA. So when we subtract, when we have VB minus VA, we must get a negative number, right? So we come over here, is it negative? B is a larger, RB is larger than RA. So 1 over RB minus 1 over RA is a negative, right? Okay. All right. So now let's we get tired of writing this all the time. This 1 over RB minus 1 over RA. Let's just pick a point and all agree that for point charges, we're going to call that point V equals 0. Because remember, with electric potential, what really matters? Changes in electric potential. So if I have a point in space over here, I could call it 0 volts. And if my electric field points this way, then over here, I must have some positive number, maybe positive 10. And over here, maybe I have has to be less, right? If the electric field is pointing this way, I have to have less, maybe negative 10 volts. I could do that, that's fine. Or I could call this point 10 volts. And then this one 0 volts, and this one 20 volts. That would work also, right? It's kind of arbitrary what I call 0. What matters when you're working problems is changes in electric potential. So if we could just all agree on what point we're going to use for 0 for point charges, then we don't have to write it as 1 over RB minus 1 over RA. We can just have a simple equation with one distance in it. So where does this naturally go to 0? 1 over R naturally goes to 0 when R goes to infinity. So we're all going to agree, let V equals 0 when RB goes to infinity. So if we can all agree that 0 potential is at infinity for point charges, then this equation just becomes V. We don't need delta V anymore. We know V is 0 at infinity. That's one of our points. So the V at any other location near our point charge is KQ over R. This is electric potential. We didn't talk about units yet. Units are the joule per coulomb, right? And we get tired of writing joules per coulomb all the time, right? It's work divided by charge, joules over coulombs. And so we write volts, V. And I think I mentioned in the other day, maybe it was in the lab, but for some reason, I don't know why we do this, but we don't do it with, I don't think we do it with anything else. You don't use the unit for to be synonymous with the item that it represents, right? We don't say what's the Newtonage acting on that object. We say what's the force acting on that object. The unit is the Newton, right? We don't say what's the Celsius of the frying pan. We say what's the temperature of the frying pan. The unit is Celsius, right? But for some reason, we sort of use volts and electric potential synonymously. So we often say, what's the voltage at this point? Or how many volts, what voltage does the battery put out? And so we use the term voltage and volts as electric potential. Some physics instructors are really sticklers. They hate that. You know, everybody does it. So just get used to it. You'll never win that battle. Everyone does it. Okay, so it's maybe a little confusing at first when you hear the term voltage and you hear electric potential and things like that, but those two terms mean the same thing. Voltage sounds cool. Yeah, sure. All right, so let's do this now. You know where we're going with this? What did we do with electric fields? One of the first things we did is we said, what's the electric field from a point charge? Once we knew what the electric field from a point charge was, then we said, what's the electric field near a charge distribution, a continuous charge distribution, where we can break up that continuous line of charge into little teeny tiny chunks, and each one of those chunks is so small we can treat it like a point charge. We can integrate and find the net electric field. So what do you think we're going to do now? We just found the electric potential from a point charge. So we're going to find the electric potential from a line of charge. We're going to treat each little tiny infinitesimal chunk of that like a point charge and integrate and add them up. So let's find the electric potential find electric potential near a line of charge. Length equals L. If V equals 0 at infinity. Okay, so because we're using our point charge technique, we've all agreed that V equals 0 at infinity for point charges. So we'll just start with that. Now we'll do this, make it on the x-axis here. So we've got there's our line of charge, and this will be L over 2, and this will be minus L over 2. And we want to know what's the potential right there. The distance A away from the center of that rod. What does it mean to have a 5-volt battery? Well, a 5-volt battery maintains a constant potential difference between one terminal on the battery, the negative side, and the other terminal on the battery, the positive side. It maintains 5 volts, and that's what it tries to do. It tries to be a constant potential source. So, yeah. So you've got if you have a battery here, this is a symbol for a battery, right? And this is a 5-volt battery. The bottom of that battery is 5 volts lower than the top. The long line is the high voltage side. So whatever this is, if this is 0 volts, call it whatever you want, then this is going to be 5 volts. If I hook up another battery here, maybe this is another 5-volt battery, it has to maintain a difference of 5 volts. So if the bottom of that battery is 5 volts, then what is the top going to measure? 10 volts. Because this is a delta of 5 and this is a delta of 5. Okay, back to integration. All right, so go ahead and set this up. It's the same techniques we used integrating over line charges to find electric fields. Now we're integrating to find the electric potential. Same technique. Uniform charge distribution, yeah. Lambda. All right, so you pick some little arbitrary point, call that dq, some little tiny infinitesimal chunk there. That means that this is dx, and this is x, and this is r. The distance from dq to our point of interest, right? So we say for a point charge, the electric potential is kq over r. So if our point charge, so the potential due to dq is dv k dq over r. That's a q. And so what do we say? We say dv is k dq over r. And we want to integrate both sides. Am I forgetting something? What's different about this? Yes. So for 2 weeks, I've been pounding into your head, vector, break it up into components before you integrate, break it into components before you integrate. Now we have a scalar. No need to break it into components. Please don't break it into components on the exam. Okay, So what do? We plug this in. R is x squared plus a squared square root. Lambda and k are constants. We are integrating over the charge distribution in the x direction, so it goes minus L over 2 to plus L over 2. And that's our integral. We look it up, get the natural log of x plus x squared plus a squared square root. Whatever that turns out to be, it's a little messy. It's a little easier if you go from 0 to L over 2, I think, and multiply by 2, but something like that. Where did the over A come from? You have ln of I combined something. Yeah. I made this 2. Yeah, I think if you do it yourself, you'll see that it works out. Okay. Got a video I'm going to show you.
I don't give 2 hoots and a holler about flying inside a helicopter. Put me outside. That's where I want to be. On the magic carpet. Back in the late 1800s, there was a gentleman by the name of Michael Faraday. He had a theory that if you enclosed a man in a metal cage and energized that cage at whatever voltage, the man would still live. The voltage would flow around him. I wear a hot suit. It's 75% Nomex for fire retardant and 25% stainless steel thread. And that metal thread means I have a Faraday cage around me. 500,000 volts pass over my body, but I can work without interference from the electricity. As long as the helicopter is isolated from ground, we have the ability to bring ourselves to the same voltage potential as the line, like a bird on a wire. pilots are very smooth. It's like they can read our every thought. There's such a hunger for electricity these days. Nobody wants to take lines out of service just to maintain them.
You'll notice the guy going the other direction has a slightly different technique than this guy.
I've had many people ask me, do you think what you do is safe? And I say, well, in our operation, everything that we do, every move that we make is thought of and rehearsed before, so it's as safe as crossing the street. It's not a job for a hot dog. There's only 3 things I've ever been afraid of. Electricity, heights, and women. And I'm married too.
Okay. Wouldn't be a good physics video without a corny joke at the end, right? But let's take a look at this. So he brings himself, he comes up close, and what we've learned is that where the radius of curvature is the smallest, the surface charge density is the greatest. It means the electric field is the strongest where the radius of curvature is smallest. So if you have sort of a pointy object like he's using, where is the air going to break down first? Where is the breakdown going to occur? Where's the spark going to strike? It's going to strike the point. So that's why he's got this pointy object there. And the air breaks down and becomes a conductor. That's what those sparks are. And charges are flowing back and forth between the helicopter and the line. And the helicopter is coming up to the electric potential of the line. There he clips it on to keep it at that potential.
I wear a hot suit.
He's wearing a Faraday
75% Nomex for fire retardant and 25% stainless steel thread. And that metal thread means I have a Faraday cage around me. 500,000 volts pass over my body, but I can work without interference.
So I think the question is, why does he need a Faraday cage? You can sit, right? The bird can land on that wire as long as the bird's not connected to ground, right? There's no place for the electricity to go. I think it's for getting on and off the wire. I think once he's on the wire, he's okay. But it's that getting on and off, bringing the helicopter up to the potential of the wire, that electricity would probably flow through him, probably enough to do some real damage. Stress, peace of mind. And then those 2 lines. So normally when they transmit energy, they transmit it in 3 phases.
Isolated from ground,
and it looks like
the ability
these
to bring
2 lines are
to the
identical, right? Because he joins them together and he's climbing
like a bird on a wire.
But if you look across the way here, there's another set of 2 lines. And then off in the back, way back in the distance, I think there's one more set of 2 lines. So normally big transmission lines come in sets of 3. It's run in 3 different phases, out of phase with itself, with 3 phases, out of sync a little bit. And so I don't know why they run 2 wires, but it looks like that's the way they do it for each phase. And now watch how quickly the helicopter loses that potential. So he's unhooked it.
It's like they can read
and as soon as it moves away, it starts to drop in potential. And I think that's all that air, right? All that air flowing over the helicopter, it just pulls the charges off and it dissipates that charge very quickly. Anyway, fun video. So let's spend the last few minutes linking what we're doing here to what we did last time with electric fields. All right, so what did we do? What did we do with electric fields? First thing we said was we can, the electric field from a point charge, kq over r squared. And then we said from a charge distribution, we can treat each little element dq like a point charge, and then we can integrate over the charge distribution, right? And we just did that with electric potential. And then what did we do? We said for certain symmetries, right? Spherical, cylindrical, infinite sheets. We used Gauss's law. So what do you think we're going to do for electric potential? For certain symmetries, when we can get E easily, use delta V is the integral of E dot ds to get delta V. When can we get E easily? When we have cylindrical, spherical, symmetry, or infinite sheets, right? And we can use Gauss's law to very quickly get the electric field. So just to review, electric fields, first thing we did, found it from a point charge, and then we said we can integrate over a charge distribution, treating each little dq like a point charge and get the total electric field. We did the same thing with electric potential. It was a little easier because we didn't have to break it up into components, but it was the exact same technique. Treat each little dq like a point charge, integrate, add them all up, and we get the net electric potential due to that charge distribution. And then with electric fields, we had this other technique. What did I write? Oops. R, not R squared. Thank you. Then we said for electric fields, we have this other technique that only works in a few special cases, but in those few special cases, it makes finding the E field very easy and quick. And now we're saying, well, if we know the E field, or we can find it really easily and quickly, then we can use this equation to find delta V between any 2 points. Okay, so that's what we're going to start with next time. Okay. This equation gives us delta V, not V. This equation does not assume V is 0 anywhere. So if you're given this this technique, usually so that everybody in the class has the same answer, I would tell you where to take V equals 0. Otherwise, everyone might have a different, as long as all the delta V's were correct, we could all have different answers and still be correct. So usually when you see this technique, it says, let V equals 0 at, and they give you some location in the problem. Sometimes it's infinity. If you have spherical symmetry, it's usually at infinity. If you have cylindrical symmetry, it's usually on one of the surfaces of the cylinder. You'll see why when we get to that. Okay. So that wraps up today. I think we'll start working more of these problems. And we've got our lab coming up. I'm going to stop the recording. I'll hang out for a few minutes, but we've got our lab coming up at 12:15, and I'll see some of you there. Okay.